I already recorded a new video for this when I thought that I was gone and you would be learning this. All right. Only 2 lessons in Unit 8. If we look at our homework, it looks like this stuff is completely different and new. I'm about to tell you why it's the exact same thing as what we just did in Unit 7. Okay? What do we learn in Unit 7? Well, we learned that when we're given a derivative, we could do a nice little sign analysis of our derivative. Negative to 1, positive until 3, negative after that. And back in Unit 3, that told me where we had max and min locations. Okay? Cool? So we've known this since Unit 3. Well, what's the new thing that we learned in Unit 7? Sure, we learned about like position, velocity, accelerating motion, but the displacement, how we could find the accumulation of my derivative. And the accumulations of my derivative, say from 0 to 1, the accumulation of x prime, that being negative 1, tells me how much I went down, a total change in my position. And from 1 to 3 tells me how much I went up. My total change, I went up 4. My x increased by 4. From 3 to 4, my total change was negative 2. How much I went down. This is what's new. Okay? This is what's new. And without even given an equation for x, just given one point, like x of 0 is 5. Could you tell me what x of 4 was? Right, because you know that if I know 1 point and I know the accumulation of my derivatives or my displacements, I can combine the two to get my new point. Okay? Hold on to this for the future. But for right now, let's focus on this. Accumulations of derivatives, changes in totals. This is the fundamental theorem of calculus. This is the whole, there's velocity times times. There's accumulations of velocities. Calculator can do this. Calculator can accumulate velocity. What can you do? You could take the antiderivative and find the change in position. 2 different ways, meaning the same thing, displacement, right? Let's kind of simplify this to just an accumulation of a derivative gives me a change in my antiderivative. Well, we're talking about x prime. The antiderivative is x, it's a change in my position. If we're just talking about a derivative, I'm going to say it's just a change in a total whatever, you know? And it's what's really important is that this applies for any derivative. What if this was f prime? Oh, okay, well, this is f prime. This would tell me about f, and this would be how much f is increasing or decreasing, right? It could be anything. It doesn't have to be x, v, and a. V was x prime. It's a derivative. Okay, so the accumulation of a derivative is a change in total. Now, what is other words for derivatives? Actually, two other words, but I'm going to add a third. Rate of change, love it. Rate of change. Okay, how quickly things are changing. That's a derivative. What's another word for a derivative? No, that's a tangent slope. A slope at a point. Tangent slope. You know what's another word for a derivative? Now, these were the only 3 that we've used up until now. I'm going to add another one. The velocity. Right? How quickly something's changing. Maybe that makes more sense to you intuitively, because we've talked about velocities a lot in our educational careers. Okay, I'm going to focus on this guy, rate. And I'm going to change this statement up. I'm going to just say, if you accumulate a rate, you get like a total. Okay. Now, the notes, we're not going to pay attention. If you want to read through them, it might make sense to you. But I'm just going to kind of skip to some space in a second. I'm actually going to go back to the problem. We're about to do part A of this problem after we realize what we actually have. R is the rate at which rainwater flows into a drain pipe. Now, it's a capital R, and this freaks a lot of students out. But R is a rate. It's a derivative. It's a velocity. What's an indication it's a velocity? Look at the units. Feet per hour, meters per second, velocity. Make sense? Okay. The derivative is a velocity. I'm going to call it a rate at which things are flowing in. Okay, the rate at which water is being added. The velocity in. Cool? Well, let's look at part A. How many cubic feet of rainwater flow in to the pipe during the 8-hour time interval? Tell your neighbor what you think you would have to do to answer that question. I kind of think, get the answer. Yeah, calculators, get the answer. Let's make sure we get the right answer. You get 76.57 something. Yeah, is that what you got? 76.57. Cool? Cool? Because you understand what you have is a derivative. And if you want a total in, which is what this is asking you for, a total in, you need to accumulate your rate in. No, you literally just say it's in cubic feet, 76.57, what's the third decimal? 0 cubic feet. You need to put that 0 down though. No, just 3 decimal places. And that's this guy right there. Okay? 0 to 8, integral, 20 sine, x squared over 35. I didn't plug in 8 for x squared. That's a common mistake made. I'm just accumulating that velocity, like I did on question 3 and question 4 when I'm given a velocity. All right, now I'm going to add another part, 8.5. Okay, I'm going to write it down here. And 8.5 is how much water is in this pipe at exactly t equals 8. Okay, and then we're going to go back to our notes and we're going to kind of write down what's going on. Okay, well, let's make sure we understand the question again. Make sure we understand the situation. We have a rate at which water is flowing into the drain pipe, but we also have another rate. Okay, so this is the difference between last unit and this unit. We have a rate at which it's going out. This d, this is another derivative. This is another velocity. This is different. I'm used to just giving the velocity. Here's my velocity. Now I'm giving 2 velocities. Okay, so that looks a little different. Sure. What else do I know? Oh, I started with 30 cubic feet of water. All right, talk to your neighbors about how would we be able to find how much water is in the pipe at a moment? What are the three factors that are in play here? Go ahead and discuss.
There's the initial amount of water. I think we can assume that how much water and it's going to be the full amount. Like, it's not going to go backwards. I think right? Can we assume that?
I'm not sure.
That it's not going to go backwards?
The rate out? No. Well, you could lose water. Ready? There's three factors at play. Now we are going to just find some space, and I think you'll find like this whole finding values of total. Don't even pay attention to anything else. Let's just like focus on this. Just find some space in your notes. Okay. And we're trying to find the total amount at a time, at a specific time. So I'll just say total amount. What are the three factors at play? Give me one. The initial amount. Okay. What's another factor? Yeah, there's water that is coming in. I'm going to say that's a total amount that has come in over that time period. What's the other factor? Well, we're losing water too. What do I need to do with that water that we're losing? Subtract it, right? Start with amount, figure out how much has come in, figure out how much has gone out, subtract the amount out from in. Okay, well, let's make this more mathematical. Okay, let's use this big capital T, and this big capital T is going to stand for the total. And I want the total amount at times 8. So the capital T is the total. That's a time. That's a T equal. Cool. Okay, what's my initial amount? Well, in this problem, it's 30, but I could say it's like T of 0. Now I need the displacement of my total. Well, my total in, I know, since I'm given a derivative, since I'm given a rate in, I can accumulate my rate in, and I get my total in. Does this look familiar to you? Does this look just like x of b equals x of a plus integral from a to b of b? Yes, but hold on, we're not done yet. We also have to subtract our total out. So that's new. The fact that I'm given two velocities and that since there's two velocities, I have two integrals at play. But that's the only thing that's new. Okay? And we'll talk about like maxes and mins, just like we talked about furthest right, furthest left in a second. So everybody please find the total amount at time 8. And you get 48 or something? What do you get, White? 48.543. Get that in your calculator so that you know that you can do this. Total in, accumulate the rate in. Rate in being a derivative, being a velocity. Accumulate velocities, change in total. Total out, accumulate your rate out. So you're given a velocity. Now, to make sure you have a non-naked answer, guys, for 8.5, you need to write this down. You need to have somewhere that t of 0 is equal to 30, or you just put 30. And then keep it simple. You don't have to write the entire equation out, but you do have to show how you got the answer 48.234. What is it? 48.543. Questions so far? Okay, so that's cool. That's like when I asked you, hey, here's v, here's x of 0, here's v, find x of 8. Oh, okay, take x of 0, add the accumulation of your derivative. One difference being we have two velocities at play. Okay, cool. But at least we know that it's like, looks fit. But let's look at part B, and actually let's go straight to part C. Part C, at what time t from 0 to 8 is the amount of water in the pipe at a min? What is this just like the question I asked you from Unit 7? Furthest left, furthest right, max min position. Great. Now for questions 3 and 4, when I asked you furthest left and furthest right, what did you guys do? What was the first step you did? Like in your calculator? Yeah, you graphed V, right? You graph V, and if I can see V, I am going to be good to go. Like you, here's the max min. You guys like graph V, because V is a derivative. And we know that the signs of a derivative tell me when the original thing is increasing, decreasing, boom, I located a max. I have candidates, right? So you guys always like, you graph V. But I have two V's. How do I graph two V's? Now you can graph them separately, but I'm not going to do that. I like to just graph V. Like you guys like to graph V and look at V, right? So I got to do that, but I'm not graphing like X prime here. For this situation, I want T prime. Okay, T prime. And I want to figure out what's going on with T prime so I can figure out when T is going to be at a max or min. All right, derivative equals 0, endpoints, candidate. Well, what's T prime? What is my velocity of T? Well, one thing I can do is like kind of change this to just be like a time. And this is something that is new, but should make sense to us. Like I could plug in any number for T here to find a total amount. Cool? It's not necessary to do this. But like, let's just take the derivative of this, right? Because the derivative of the left is just T prime. Okay? Okay, let's see if this makes sense to you. T of 0 is just initial amount, it's a number. So what's the derivative of this initial amount? 0, very good. Okay, so that's gone. Now, this is new and we're doing more of this next class. What's the derivative of this integral? Yeah, so like the integral to you means anti-derived. If I take a derivative of an antiderivative, doesn't the derivative and the antiderivative just like disappear? Yeah, exactly. That's what happens. So, oh, okay, there's one of my velocities. My derivative is my velocity in. The minus stays. The derivative and the antiderivative cancel each other out. What do I have? My velocity out. Oh. If I have two velocities, one's a velocity in, one's going out, combine them by subtracting them. And that's your velocity that you can graph.
Is it still D over D?
Yeah, you're still dt. Okay. We're still doing time. Now, that means in y equals, for this situation, to answer part C, T prime is the entire equation R of T minus the entire equation d of t. That's a lot to type into y equals, but that's what you have to do. That's my velocity of my total. This is the derivative. This is t prime. Okay, let's do it. In y equals, type in r minus, and in a big old set of parentheses, d. Velocity in, velocity out, two velocities at play. Well, subtract the out from the in. You have the overall rate of change of the amount of water in your pipe. Okay. You guys took 0 to 8 of R, you got 76.57. 0 to 8 of D, you got 58.026. You took 30, you added that, you subtracted that, you got 48.543. In y equals, we graph R minus, and in a big old set of parentheses, D. Okay? Cool? Now, here's what everybody does. They press graph immediately after typing it in, and then they realize, oh no, I don't want to look at the entire graph. Okay, press on. Pause this thing. This is a nice, helpful hint, because everybody messes up on this, okay? Everybody immediately types graph, and then you're like, oh no, I have to change the window. You have to wait till it graphs the whole thing. Well, press on and it pauses. Cool? All right, what do we want? What's our interval? 0 to 8, just like a time interval from last unit. Now, y mins and y maxes, we are comfortable with keeping things from -10 to 10 last unit, just because that's how I kind of designed it. But some of these rates are going to be bigger numbers, okay, these velocities. So, you guys remember how zoom fit works? Zoom fit adjusts the y. Zoom fit is zoom 0. Adjust your window first, that adjusts the x's, and then do zoom fit, that adjusts the y. And now you see what you saw last unit for question 3 and 4. You see v. This is t prime. Great. This is the derivative of my total. This is what I analyze to figure out when things are increasing, decreasing, when we have maxes, when we have mins. We find our candidates. One's at 0, one's at 8. One's at this value A. What is A? Find it. Everybody find it. Do you remember to graph y equals 0 as well? Yeah, it ends up being 3.27. Find it. Does yours not look like mine? That first thing is a negative. Yeah, enter a negative. Okay, that's good. Yeah, that's good, man. No, I'm not. -0.04. Now, there's a lot of stuff we're typing into our calculator, so you got to make sure you type it in right. Okay, second calc, intersect. Enter, 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 boom. All right, so we get t prime equals 0 at t equals a, which equals 3.2716584. Now, hold on, guys. This is a free response question. They want me to justify my answer. What do I need to write down on my piece of paper? This is good practice. Write it down. See if you can do it right. And then I'm going to tell you if you're wrong or not. What do I need to write down if I'm asking for the minimum amount of water? Write it down. What do you have to write down? Tell your neighbor. No. Of 0 of what? Yes, you have to write down. T is a min when T prime equals 0, or an endpoint has to be written down. This is the extreme value theorem. You don't have to reference this is the extreme value theorem, but that's the extreme value theorem. You have to write that down. Didn't I yell at you guys to write that down on Wednesday? Yeah, okay, we'll write it down. Now, you need to compare your candidates from this statement. T of 0, what's that? Good. T of 8, because I told you to do it, you already have it. You don't need to show the work. Well, everybody find T of A for me. And are you writing down what you should write down so that you don't have a naked answer? Well, if you are, you're writing down either 30 or T of 0 plus accumulation from 0 to A of R minus accumulation from 0 to A of D. You already used it. You got X, you store it as A. There's that 3.27165845. Arnold. So you could do integral from 0 to A of T prime. That's fine. Yeah. I like to keep them separate, Arnold, because for some of these questions, a rate in's from like 0 to 6. But the rate out is only from 2 to 6. And it's in those situations, Arnold, that having them separate is very beneficial. Okay? All right, so I go from 0 to A, I get 6.625. Now I know what 0 to A of D is going to be in comparison to 0 to A of R. Did you guys think about this? I know that this is going to be a bigger number. Why? Because T prime was negative, meaning T is decreasing. I must be losing more water than I'm adding, right? Maybe you thought about that, maybe not. Add those three things together, you get 27.964. You circle this, you say, hooray, I found my min. Using the candidates test. But I'm about to tell you that me screaming and yelling at you guys to write this statement down and all of this work that we just showed, it's helpful. It can always be used, but it's not needed for this question. Why? Why? Let's go back to the question, part C. At what time T? Did they ask you for an amount? Are you asked for an amount? No, you just asked for a time. Okay? Because I'm just asked for a time. I don't need this. Why? Because it has to be A. This has to be the min. Because T is going down and up. It can't be an endpoint. Endpoints can't be candidates. But, Mr. Master, you told me that we can't use this. Sure. Sure. But I can say D equals 3.271 is the min because T prime is negative from 0 to A, as long as I have A written down. And then T prime is positive from A to 8. And yeah, are we using this? I mean, yes, we are, but we're writing down what it says and what it means. And then all of a sudden, we have the same answer, but maybe a little bit less worked up. Now, I don't like when I tell you guys, like, here's multiple ways to do the same thing. The candidates test always works. It can always be used. However, if you guys think conceptually about what's going on, if you think conceptually about what you see here, maybe you don't have to do as much work. Okay? So maybe think a little bit more about what do you see. Maybe you write down your sign analysis of T prime. It's negative and positive. A's got to be the location of a min. I just confirmed it. I did the candidate's test, but didn't need to do it. All right, go back to part B. Is the amount of water increasing or decreasing at T equals 3? And then I'm going to ask you by how much? Any questions? Wheeler, you good? Are you sure? Oh, sure. Well, you could have just asked. Yeah, go back to B. Answer the question. But I'm adding something to B. The amount of water in the pipe increasing or decreasing by how much? What? Oh. So good question. If I asked you, is the rate increasing or decreasing? Is the rate of change increasing or decreasing? I'd look at T double prime. And there are some questions on this homework where they ask you that crazy worded type question. Is the rate increasing or decreasing? You'd have to look at the slope of T prime. But this is just, is the total increasing or decreasing? Is the total increasing or decreasing? Well, I know that 3 is to the left of A. I know T prime is negative at 3. So it's decreasing. But by how much? What's T prime of 3? Well, either in the graphing screen, you can just find T prime at 3. Use trace, go to 3. You get negative 0.313. This is telling me T is decreasing by this many cubic feet per hour. What's the other way to do it? In your home screen, you find R of 3 minus D of 3. Remember, R is already a derivative. This is a common mistake made. People think they need to take a derivative to find a rate of change. Guys, you are given derivatives. You're given velocity. So, T prime is R minus D. T prime of 3 is not R prime minus D prime. It's just R of 3 minus D of 3. That value, negative 0.313, is literally 20 sine of 64, of 9 over 35 minus, and again, this is going to take a while, but whatever, negative 0.04 times 3 cubed plus 0.4 times 3 squared plus 0.96 times 3. All right. Cool? That's something in wrong. Okay? Great question. Great question. Great. I know. That's what a lot of people do. But remember, you're given the derivative. You already wrote down somewhere that T prime is R minus D. It's not R prime minus D prime. Okay, it's my velocity in minus my velocity out. In your notes, you circle these two equations. This is all that you need to know. And it's the only thing different about this from last unit is the fact that there's two velocities. And then you have to subtract the out from the in to give you an overall velocity. This is it. Okay? Now, you ask the question, when do you have to take the derivative of R and the derivative of D? Well, if I ask this question, and this is part E, we'll come back to part D. Is the rate of change of the water increasing or decreasing? Okay? If you look at the elevator problem, this problem, no, that's not this problem. Where did I see this? The fish problem? The fish problem. Fish in a lake. I know. You're going to have fun with this, guys. Is the rate of change of the number of fish in the lake increasing or decreasing? Okay? Okay? Ready? Remember, guys. T prime tells me if the total is increasing or decreasing. That doesn't answer this. T double prime will tell me if the rate of change increases or decreases. This is when we go to the second derivative sign analysis. So going back to the problem at hand, the water in the pipe problem, not the fish problem, not the escalator problem, the water in the pipe problem. If I ask you, is the rate of change increasing or decreasing? You need T double prime of 3, which is R prime of 3 minus D prime of 3. Oh gosh, I have to take the derivative of R and take the derivative of D? That's gross. It's like sine of T squared. No. What's an easy way to do that? What's an easy way to find T double prime of 3? Graph. Here's T prime. Find the derivative at 3. 1.03. T double prime is positive. T prime is increasing. The rate of change is increasing. Remember that? Cool with that? Remember, your calculator can approximate tangent slope. Could you take the derivative using the derivative rules of R, and you get 20 cos T squared over 35 times 2T over 35, chain rule, and D, negative 0.12 T squared plus 0.8T plus 0.96. Plug in 3 into that and plug in 3 into that. Subtract them, yeah, you get the same answer. Okay? But let's go to part D, because part D is actually different. And like, the part Ds are usually where people get all freaked out. Because you haven't seen this before, but I'm going to show you that. If you have these two equations down, like, this is what's going to lead you to victory. And maybe a third if you want to. For that extra bit. Okay? So let's read the question. It's the pipe can hold 50 cubic feet of water before overflowing. For T is greater than 8, water continues to flow into and out of the pipe at given rates until the pipe begins to overflow. Write, but do not solve. That's important. An equation involving one or more integrals that gives the time W when the pipe will begin to overflow. Yikes. Where do I start? Okay. When will the pipe overflow?
When the rate, wait.
No. To the question.
The rate in has to be more than the rate out.
When it's greater than 50. Pipe will overflow if the amount of water is 50. Okay? The pipe will overflow when the total amount of water is 50. Find an equation, or write an equation that uses W times W. What? Well, I guess time W. Okay, T is W. Okay, T is W. All right, I win. I'm done. It's like, well, Mr. Smith, like, what do we do? Like, nothing. Like, you're done. You're done. You don't have to solve this. Here's an equation. It involves integrals. It's got W in it. Now, how would I solve it? In a hypothetical world, I would take the antiderivative of this, plug in W and plug in 0. Take the antiderivative of this, plug in W, plug in 0. Simplify and solve, probably not going to be able to be done. Graph y equals this side, graph y equals that side, find the intersection. Okay, that's more realistic. Unfortunately, I can't take the antiderivative of sine t squared over 35. Can't be done. You guys don't know how to do it. You could take the antiderivative of d, but let's not waste our time. Okay? Done. I'll call it. All right? The rest of the questions are just like this, with some differences. Let me tell you one quick thing about a difference. Let's look at the escalator problem. Ready? Ready? This is important. Ready? Ready? Escalator problem. Sorry, I said I was done, but I wasn't. Because this is a big mistake students make. People enter in a line for an escalator given by R. This is a rate. You read that rate. You know this is a derivative. This is a derivative. That spells derivative. That's a rate in. People exit the line at a constant rate of 0.7 people per second. That's just a number. So that's a little bit different. And again, that's my rate out, but it's just a number. Now, lesson 2 of unit 7, I started with this question. If my velocity is 70 miles per hour and I'm driving for 2 hours, how far did I drive? 140, right? If your rate is constant, it's easy to use. Like 0.7 times 300 is a total. That's one way to think of it. Or finding your total, like at 300, yeah, you got an initial amount. You have a total in, which is your accumulation of your rate in. You need to subtract your total out. Now you're used to an accumulation of a rate out with this being an equation. It's just a constant. It's okay. Just put 0.7 there. What a lot of people do is they think more of like, oh, velocity times time, and they put 0.7 t in here. Okay, but that's actually the derivative. That's actually how you're going to accumulate your velocity. That's like 0.7, that's 70 miles per hour times 2 hours. So either use this, and I explained this in the video, and use this and be okay with it. Or understand that this is the same as 0.7 times the time. It's the same thing. It's like accumulate 0.7 over 300 seconds. Remember, this accumulation is like the area. If you're doing 0.7 over 300 seconds, you're just multiplying the two to get this area. That's a rectangle. This and this are the same. I'll prove it to you. 0.7 times 300, that's how many people exit the line, 210, is the same as accumulating the rate not of 0.7 t, but of just 0.7. Accumulating this, just a rectangle worth of area, and you get 200. Okay, so safest to use this. Just don't add a t in there. A lot of people do. All right, cool.